All right, cool. So for this one, the answer is interacting with fatty acid tails in the interior of the plasma membrane away from the watery intra-extracellular membrane or environment. So just remember, this is a hydrophobic molecule. It's going to be where hydrophobic stuff is. And in this situation, that's the inside of the fatty acid membrane. Cool. So this second question, okay, so this wants you to know the inside and outside of a protein and how it would basically be configured going through blood. So the answer to this one, the outer surface is hydrophilic and the interior is hydrophobic. Once again, this is kind of the same principle we just covered in question one. So let's say we have this protein glob and it's going through the blood, and the blood is mainly hydrophilic. The outside of the protein is going to want to be hydrophilic, and everything that's hydrophobic will get kind of pushed towards the interior. So what that would look like, we're just going to do, we'll just do pluses and minuses and pluses and minuses.
Are you writing on the screen right now?
Yeah, can you see it?
No.
No, we can't see it.
Okay, hold up. Now can you see it?
Yes.
Okay,
But like
cool.
but we just see like your OneNote, not the actual
Can you see the notes I'm taking?
Yeah, you're doing squiggly lines.
Okay, yeah, cool. So these pluses and minuses, that's just hydrophilic, that's stuff in your blood. And then we have this protein. Here's the globular protein. This protein is going to put all of its hydrophilic stuff on the outside. So it's in contact with other hydrophilic stuff found in the blood. And then all the phobic stuff will be on the interior. Does everybody understand how proteins modify based on the environment they're in? Okay, sweet, sweet. So let me know. Are we back? Can you guys see the question now?
Yeah.
Okay, sweet. So for question 2, it was the outer surface. Hold up, we'll go through and click all these off. All right, cool. Question 3. And these questions are big too. There's like some big paragraphs. So I didn't memorize them all, so I have to reread through them a bit. Okay, so the really important part in this is that these are just becoming overly swollen or completely bursting, which means it's hypotonic saline. So tonicity can get kind of confusing. Basically, these cells are hypertonic to the solution, but the solution is hypotonic to this cell. So what this means is the cell has more solute in it, and so the water is going to follow that, and it's going to all go into the cell, and the cell is just going to swell up with water. So for this, just remember that water follows the solutes. So a good like real world example, albumin is a protein in your blood, and albumin basically plays a large role in the osmolarity of your blood. So if you have a lot of albumin in your blood, it'll bring water into your vascular system and increase your blood pressure. Another one is like you don't really use it too much, but you can have a hypertonic saline solution and give that to somebody, especially if they're in like hypovolemic shock. So that's kind of the concept that this question is getting after in a real world situation. So now we'll go to 4. basically this is just hammering on your knowledge of cell membrane permeability. The answer to this one is 1342. So remember that your hydrophobic stuff is going to go through a lot easier. Your things that are polar are usually going to need some type of transport, whether it's a passive like a channel or it's active like a pump or something like that. Symporters, antiporters, they'll need that to get through. Does anybody have any questions up to this point? Cool. So this one, the white circles are O2. So remember, oxygen is one of those things that can kind of just diffuse through a plasma membrane. It's a diatomic gas and it doesn't really get held up too much. It'll just zip right through. So the answer to this one is no, this membrane protein is not necessary to transport O2. If you look at this protein, it looks like a channel. So that would be good at transporting other things. All right, so I'll give you guys a second to read this question, and then we'll work on it. So the first thing you should do when you see this problem is just kind of understand what's going on. So if you look at time point 0, you can see that there's a lot more outside the cell than there is inside. And then skip down to time point 3, and you can see they're equal. So let's say time point 3 was the last marked thing we did. This would just be a simple diffusion or something like that because it gets to equilibrium and it stays there. But since we keep pumping stuff against, look at time point 4 and time point 5, we're now going against the concentration gradient, which is going to require active transport, which means there's some type of energy being used. There's ATP, there's a pump, something going on. So this is false. This doesn't illustrate passive transport. This illustrates an example of active transport. And like I said, if this stopped at time point 3, then it would be passive transport because it just gets to equilibrium and stays there. So this is question 7. Same kind of table. It's the same exact table. So now it's asking you basically the exact opposite of what the last question asked. So this one is true. Did I mark that last one? So this would require a protein transporter. You can also tell that this would require a protein transporter because of how all the polarity in this molecule. This would have a very difficult time squeezing through that hydrophobic membrane. And try to remember the hydrophilic part of the lipid membrane is pretty thin compared to that hydrophobic part. And that's why this would have trouble going through so much hydrophobic material. It would just get spat out every time. Okay, so this one is asking, are any ions in this figure being moved against their concentration gradient? So this is very easy. It's just an image analysis question. You're going to be looking at these and seeing. So this one, look at protein transporter number 2. Here we can see these circles getting pushed from a low amount to a high amount. And we can also see these black triangles getting pushed from a low concentration to a high concentration. So both ions A and B are going against their concentration gradients. When you get an image like this on test day or whenever, always make sure to look at this image and really understand it before you even go to the questions or the answers. So like when I read this, I would try to think what the answer is before I even look at the answer choices. Protein 2 is most likely an active transport pump. Okay, so we know active transport pumps push things against their concentration gradients, and that's definitely happening here. Actually, in both the directions it's pumping is against the gradient. Okay, so now we're on 10. So this is asking if the movement through protein transporter 1 requires the input of energy. So let's look at protein transporter 1. We can see that what it's transporting is ion A, the black triangles, and it's transporting them from an area where there's a high concentration to low concentration. So because it's going from an area of high to low, we know that this is passive, and it looks like the only thing it requires is a protein channel. And the protein channel just kind of gives the ion safe guidance through the membrane. So this does not require the input of energy outside of the energy that was needed to create the protein transport in the first place. All right, number 11. Okay, so this one. So graphs are kind of tricky, actually. We'll do this. I'll kind of show you guys a good way of cruising through this. Can you guys see the OneNote that I'm on?
Yeah.
Yes.
Nope. All right, so when you're approaching graphs like this, all right, we see, so right off the bat, I would just do site 1, 2, 3, and 4, and write what they would need to be. So site 1, this needs to be philic, short for hydrophilic. Site 2, this is an outside portion that's in contact with these hydrophobic heads or tails. So this is going to need to be phobic. Site 3, this is the inside of the protein that needs to be okay with transporting water. So for that to happen, 3 needs to be philic. For site 4, we're in an aqueous intracellular space, so this also needs to be philic. Now, some of you guys can just look at this and automatically think like, okay, 1 is philic, 2 is phobic, and you can just look cross-reference with the graph. But writing it down kind of is a fail-safe, and it'll prevent mistakes. 'Cause sometimes when you're going fast, you just mess up. So then we go here. Site 1 needs to be philic, so that ruins this and this. So A and C are already canceled out. Site 2 needs to be phobic. Okay, this doesn't have that. Boom. So we know right away it's a D. Go back here and mark it. And we went through that kind of fast. Does everybody got a grasp on that? All right, so now we're on 12. So based on the movement of water, this is kind of like what we said earlier. Based on how the water is moving through the cell, we know that the water is following the solute. Oh my gosh, I can't freaking speak today. So that's where it's at. The solute is high inside the cell, and it's a lot less outside the cell, and that's why the water is going to move into the cell. So you could say if the inside was your bloodstream, there's a lot of albumin, and water is going to follow that. I mean, there's other things that bring water into the bloodstream. I just keep saying albumin because that's what we just got done studying in anatomy. But I mean, sodium, Antidiuretic hormone brings water in. Cool. So this graph, I know last year this was really tough for a lot of people to understand what's going on. There's really three big parts with this graph. Does anybody not have a good grasp on this, or would you like to understand it better? All right, cool. This is a pretty complex graph. It took me a while to just kind of look at it and break it apart to understand it more. This looking at graphs like this and understanding this requires like a unique way of looking at things, but it's extremely useful. I keep saying it, but understanding stuff like this is going to help you a ton when you take the MCAT or whatever future test you plan on taking. So basically on this one, we have glucose would no longer be able to flow from the lumen. Okay, so if we stop structure A from working, structure A brings glucose into the cell. And it also brings sodium in. Oh, so if we stop that from happening, there's going to be less glucose in the cell. And then that's going to ruin the concentration gradient. So then glucose won't leave into the bloodstream. And that's basically how that domino effect will apply to the bloodstream. So this one, they made this mouse that has a NA channel in the basal membrane. So I'm gonna actually screen clip this one out so we can. Cool. Is everybody looking at the OneNote? Can you see it?
Yeah.
Okay. So let's say we're gonna put a sodium channel right here. This is our new sodium channel. This is gonna let passive diffusion of sodium take place. So can someone tell me what sodium's biggest role is in this entire thing? Okay, so the role of sodium is to leave the cell. So this pump right here, this one, is pushing sodium out of the cell. And what that does is it creates a gradient for sodium. And then this symporter, sodium takes advantage of that gradient, and it also brings a glucose with it. So the sodium gradient is very important for getting glucose into the cell. That gradient is maintained by this protein right here. So this protein maintains the gradient. And then because of that gradient, this protein can bring glucose into the cell. So now let's say we put this protein channel here that just lets sodium flow freely into the cell, into the bloodstream. It's at equilibrium. Well, that's not really going to create much of a gradient for this one to work. So once we put this protein in, there's going to be a significant reduction in the blood glucose levels. Did I mark? Okay. Does everybody understand that one? Because that graph requires you to really understand this pretty well.
So the sodium has to be present in order for the glucose gradient to be there as well.
Yep. Yeah, so sodium has to be there for the glucose gradient to be there as well. Because without the sodium, this symporter would never happen and glucose would never actually go into the cell.
So is that also relevant? Let's say it like wasn't sodium or something, but since both of them are going through, like the two gradients rely on each other.
Yeah, the two gradients definitely rely on each other. If you were to remove one, the other wouldn't be able to function. So let's say we remove the sodium gradient, which is kind of what we just did by inserting that channel. Then we would lose the sodium gradient and there'd be more sodium outside the cell. And then between the bloodstream and cell, it'd be the same. And then glucose wouldn't come into the cell. If we remove the glucose gradient, which removing the glucose gradient would be really hard to do, but basically it'd be more glucose in the lumen of the gut and none would get brought into the cell.
Okay, thank you so much.
Yeah, sorry, it's really hard to explain this model that we're looking at with a theoretical concept that we're just trying to think of on the spot. So I don't have any really good examples. The best examples I could say are other systems that work similar to this. I think if you look up, dang, it slipped my mind. It's an AB toxin. It basically causes a ton of diarrhea. Anyways, it's no, it's not C. diff. I'll think of it, but it basically uses the same thing. It takes advantage. It produces a ton of cyclic AMP, and it makes water just flood into the lumen of the gut, and then that excess water in the gut is actually what causes the diarrhea. But kind of nasty, kind of cool, and it's relevant to that. Okay, so this next one, I'm just gonna, okay, so we have glucose and it's rapidly phosphorylated once it's in the cell. Does anybody know why this would happen? Anybody? Okay, so this is to trap it inside the cell. When you add that huge polar region right there, first of all, there's no way this is going through the cell. But with this, it will prevent it from going through transporters. So if you go up here, you see this transporter, how glucose can also go out the cell into the bloodstream. Well, when it gets phosphorylated, that ain't happening. These protein channels are extremely specific. It's not just like a freaking tunnel that you drive through and there's like semi trucks and cars. Like these things are very specific. So if it's not the exact year, make, and model, it's not going through. And so that's why once we get glucose 6 phosphate, it's not going through. It'll be diverted to other processes. All right, question 16, another massive paragraph. These massive paragraphs suck. So just go through and find your keywords. Okay, it's large, it's a polar molecule. Okay, boom. Initially, so we have an initial point. It was lower in the cell compared to outside the cell. Okay. And then it increased inside and outside were equal. Okay, so we had this concentration gradient that was there, and then it became equal. So it found equilibrium. ATP concentration did not change. All right, cool. So we met in equilibrium, which I don't know, it could be a couple things, but then now that we know ATP concentration is the same, then we know that this was some type of diffusion. And so why would it be facilitated diffusion and not simple diffusion?
Is it because they're large polar molecules?
Yeah, yep, exactly. So be careful you don't just read this last little section right here and be like, oh, that's simple diffusion. Click this and keep going. Because this right here, large polar molecule, that's going to need a protein to go through. So it's facilitated diffusion. So just take your time. Like, I don't know how long you guys got on the test or how many questions it is, but you got enough time to like really read, take your time, just get a good grade. Okay, so this is the last question. Once again, we're just ranking based off permeability. Oxygen is a gas, it's a diatomic gas, it's going right through. Estrogen, very hydrophobic, it's going to go right through. Acetic acid, pH 1.5, and then acetic acid, pH 7.0. For the 1.5, it's less polar. The 7.0 has this negative charge on it that's going to it's going to have a lot of trouble going through that hydrophobic region. And that's basically it. We went through this kind of fast in like 30 minutes. Does anybody want to go more in depth on any of these questions, any of the concepts? Are you confused about anything? Because we can take some time like breaking these concepts down way more if you want to.
I don't know if you can read the chat, but someone asked to go over 16 a little bit more.
16?
Yeah.
Okay, for sure. All right, can everybody see my OneNote?
Yep.
All right, so we'll just read through this. Suppose you're studying the transport of a certain large polar molecule across the membrane of cells. Over a period of time, you measure the concentration of a large polar molecule inside and outside of the cell. Okay, so we're measuring inside and outside. You find that initially, the concentration of the molecule is lower in the cell compared to outside the cell, but the concentration inside the cell is gradually increasing over time until the concentration of the molecule inside and outside is approximately equal. So we'll do it inside, I for inside, O for outside. Initially, we found it was lower in the cell, so we'll say it's 5 and then it's 15 out the cell. But then at the end, we find out that it's equal in both. So because these are equal, it reached equilibrium and it stayed at equilibrium. One thing we know is that this isn't a pump that's involved. Because if it was a pump that was involved, it would basically push things against their concentration gradient, which isn't happening here. Okay, so now let's get the second piece of information. You also measure ATP concentration and find that it's not changing. So because ATP is not changing, this further backs what we initially thought, that we're not working with a pump here. Okay, so we know that this isn't active transport because ATP is staying the same. Okay, so now we're down to facilitated diffusion and simple diffusion. So for this, we're just going to look at this right here. This section right here is what answers the question for you. It's a large polar molecule, so it's going to need facilitated diffusion, not simple diffusion. The reason it needs facilitated diffusion, here's a protein right here. And then here's your lipids. So this big protein is going to need to come through this channel in order to get through, because it's a large polar molecule here. We'll draw some, we'll put some partial charges on it. So it's going to need that pump to go through. I'm trying to pull my screen down to check the chat. Okay, Gabriella, did that answer that for you a little better?
Yep, that clarified everything.
Okay, hell yeah. Does anybody have any other questions or concepts? Anything off this that they feel they need to know a little bit better before the test day? Okay, cool. If everybody feels good, then I think we can wrap it up. I'm gonna hang out until everybody leaves, and if anybody has any questions, just feel free to hang out.
Thank you.
Yep, you're welcome.